Antimatter is a unique form of matter in that it holds a fascinating place in the world of particle physics. Imagine the world of particles, the tiny building blocks that make up everything around us. In this world, there are particles we're familiar with, like protons, electrons, and neutrons. Antimatter introduces us to a mirror image of this particle world, where everything is almost the same, but with a crucial twist. In the realm of antimatter, each familiar particle has a counterpart known as an antiparticle. For example, the antiparticle of an electron, that being a negatively charged particle, is the positron, a positively charged particle. It's like having a mirror particle for each one we know. The catch is that these antiparticles have the opposite electric charge compared to their normal counterparts. When matter and antimatter meet, something extraordinary happens. Let's take an electron and a positron as an example. When they approach each other and mix, the mass of both particles is converted into energy, following Einstein's famous equation, E equals mc squared. So what would happen if they touched? Annihilation. If we theoretically took half a kilo of antimatter and mixed it with half a kilo of regular matter, then we would get this number of joules, or about 21.5 megatons of TNT. Compared to the Hiroshima bomb, which was 0.015 megatons of TNT, that makes the explosion caused by the mix of antimatter and regular matter 2,000 times stronger. Just to put it into perspective of how much destruction would happen if the two of them were mixed. Now let's step into the realm of high energy physics experiments, such as those conducted in massive particle accelerators. This is where the creation of antimatter happens on Earth. In these experiments, scientists can create antimatter particles by colliding high energy particles together. The creation of antimatter in a controlled environment gives the researchers a way to study these elusive particles and understand their properties. Antimatter isn't just a subject for physics experiments. Let's just look at the antiparticles of an electron. In medical imaging, positron emission tomography, also known as a PET scans, utilize the unique properties of a positron. A small amount of positron-emitting substance is introduced into the body. When positrons encounter electrons, they annihilate, producing detectable gamma-ray photons. This process helps create detailed images of the internal structure of the body, aiding in medical diagnosis. Going back to the cosmos, while we do have some understanding of what antimatter is, there are still some mysteries left unsolved. The mystery lies in the fact that the observable universe seems to be predominantly made of matter, with antimatter being relatively scarce. This asymmetry raises intriguing questions about the conditions in the early universe and the process that led to the increased amount of matter. It is believed that in the early universe, there was an equal amount of regular matter and antimatter. Similar to the cosmic microwave background, we use antimatter to look at the early universe and what happened in those early moments. While antimatter is highly intriguing, there are still mysteries left unsolved that are still being researched and discussed today. But one thing is for certain, in that the topic of antimatter provides a crucial role in cosmology about the conditions of the early universe.